everyone, my name is Pierre Weiss and I am a CNRS researcher from Université de Toulouse. And today I will present you an overview of the sampling reconstruction problem in magnetic resonance imaging. So the objective of this work is to either improve the image resolutions for a fixed scan time, or alternatively to reduce the scan time for a fixed resolution. And this has a number of assets, such as better understanding some pathologies, to reduce the costs, to reduce motion artifacts, and to improve the comfort of the patients. And there are different ways to do that, like hardware ways, for instance, by increasing the magnetic field strength. But here we will rather focus on signal processing techniques by improving the sampling strategy and the reconstruction method. So I will first present a simple acquisition model for magnetic resonance imaging, and then I will turn to theoretical result with the Shannon and compressed sensing theories. And finally, I will review some method to learn how to sample and reconstruct images. So what I will present owes a lot to discussions with some people. First, there is Michael Poole, who is working at Hyperfine now. Carole Lazarus, Philippe Sussiou, who actually invited me here, and thank you very much, and Alexandre Vigneault. So, in an idealized mathematical model, an MRI system allows to probe the Fourier transform of an image. So in my presentation, I will let you denote an image, which can be two-dimensional or three-dimensional. Omega is the domain of the image. And the MRI system allows to measure U hat of xm, where xm is a sampling location and U hat is a Fourier transform. And what you find a lot in the literature is that the sampling locations should belong to ZD, to a grid, the idea being that then you can use the fast Fourier transform. But in my talk, I will also review methods where the xm are off the grid, they can belong to all of RD. Okay, so here is an illustration. You have a brain slice, its Fourier transform, and the sampling scheme. So the white dots are dots that will be sampled. They correspond to the xm. And typically, you would expect to sample the K-space center more densely than the outer part. So this model is not enough because you cannot probe efficiently samples independently from each other. They are sampled along continuous trajectories. So a trajectory can be seen as a function from 0t, where t is the sampling time, to RD. And the trajectories in MRI must have a bounded speed and a bounded acceleration. And so given a sampling period delta t, the measurements you obtain, ym, are the Fourier transform of u evaluated at lambda of m delta t. So it's really like as if you were driving a car with a bounded speed and bounded acceleration, and the sampling problem is to recover as much information as possible within a given time t. So here is an illustration. You have a pulse sequence that generates a spiral, and the spiral is sampled with a sampling time delta t, leading to the measurements indicated as red dots here. Okay, finally, in MRI, the signal decays over time at an exponential rate, and you need to use multiple trajectories to cover the K-space sufficiently densely, and the sampling time is proportional to the number of trajectories. Okay, so I'm ready to set up the mathematical model. So I will let X be the set of sampling location, X1, Xm, and A of X denotes the forward operator, which to an image U associate its Fourier transform at the locations Xm. And usually your measurements Y suffer from noise, for instance, from additive white Gaussian noise, but you could have more complicated models, but here I will stick to this. Okay, and the complete sampling problem can be formulated as follows. So you are given a family of signals, calligraphic Q. You can think of this as the space of pen-limited signals, the space of sparse signals or a database of signals. You are given a family X of admissible discretized trajectories. And what you want to do is to minimize some cost function. You want to both optimize the sampling set and the reconstruction mapping. This is very important. In sampling, we want to optimize both things together. And the reconstruction mapping is a function which, to a measurement y in cm and to a sampling set x, associate a reconstructed image in L2. Okay. And how is this cost function defined? So typically what you would like to do is to get the best possible reconstruction. So when you reconstruct your image U from its measurements, you would like it to be close to U, for instance, in the L2 sense. And then you want to sum these errors over your family of images is U, and to take the expectation of that over all the possible noise realizations. And this gives you a very complicated cost function, which is actually extremely hard to optimize. And so now I will review how this problem was tackled from a theoretical point of view with two theories, the Shannon sampling, the Shannon theory, and the compressed sensing theory. And here what I will present owes a lot to the previous people I mentioned, but also to those ones, Jérémy Bigot, Nicolas Schoffer, Jonas Kahn, and Claire Boyer. Okay, so first I will review the theory for linear reconstruction, and in particular, Shannon sampling theory. So there you have a nearly comprehensive theory, and you know that a good sampling set should have a controlled maximal distance and minimal distance. So the maximal distance means that you should have no point in the k-space that is very far away from the sampling set. And the minimal distance means that you should not have 2 points very close to each other. And the reason is that then you can show that the reconstruction mappings things become unstable. And if you follow the simple rules, what you realize is that the optimal sampling pattern are not the Cartesian grid, as one may think, but rather the hexagonal grid, which paves the k-space more uniformly. Okay, this is the theory for linear reconstruction. And now for sparse reconstruction, here it is. So it's compressed sensing. And there you are given an orthogonal transform, psi, for instance, a wavelet transform. And you assume that your image U can be decomposed as psi alpha, where alpha is sparse. Okay. And importantly, the sparsity can be structured. Typically, if you think of a wavelet transform of an image, the sparsity increases as you go higher in the wavelet subbands. Under those assumptions, you can try to reconstruct your image by solving this L1 problem. So basically, you want that the Fourier transform of your reconstructed image psi alpha evaluated at the sampling point x is consistent with the data. So this is equal to y. And among all the signals that satisfy this constraint, you want to pick the one with the minimal L1 norm. And this idea was explained from a theoretical point of view by Candace, Romberg, and Tao, was used a lot by Lustig, Donoho, and Poli. But there I really want to mention that these papers are far from explaining the success of compressed sensing in MRI. And if you want to see theories that are much closer to the actual practice, you should switch to those papers. One by Adcock, Hansen, Poon, and Roman, and one by us, Boyer, Bigot, and Weiss, where we really explained why and how we should sample more densely the k-space center, and why it works in practice. So what is proved in ZD, in compressed sensing, is that the optimal way to generate a sampling set is to draw the points here, xi at random, xm at random, independently with a certain density that is higher at the center of the k-space than in the high frequency. Now, if you work in RD, the situation is a bit less clear. I don't think that the theory is complete yet. But what we know, at least from practice and somewhat by theory, is that the samples should not be too close. So if you just draw your samples according to a density pi, you would typically obtain this, where you see that you generate clusters. And a much better sampling pattern with the same density would be this one, where you have more evenly distributed samples. So how to generate those sampling patterns, I will explain that. But first, let me say a word that is not so common. So are Shannon and compressed sensing so different? I am not so sure, at least in terms of what a good sampling set is. So, because in both theories, a good sampling set should have a given density pi, which is uniform in the case of Shannon sampling theory and non-uniform in the case of compressed sensing, and respect minimal and maximal spacing between the samples. Okay, to formalize this problem, you can view the sampling set X as a discrete probability measure. So you construct a probability measure as a sum of Dirac masses located at the sampling point Xm, and you divide by 1/m to normalize the measure. Then you take a distance between probability measure. And what you can do to generate a sampling pattern is to minimize the distance from this measure to a target density pi, which can be known analytically from theory. And for D, you can typically take a discrepancy or the Wasserstein distance. And it turns out that this problem is really complicated, but you can compute solutions with simple gradient descent. And this was proposed by people in computer vision from Germany, like the group of Weikert or the group of Kabi-Scheidel, where they showed that this kind of dynamical system was able to solve this problem accurately. And here is an illustration. So this would be pi, the target density. This would be the resulting measure, mu of x. And the way we obtained this was by running this dynamical system. And here you see how it evolves with time. Okay. And after some iterations, you get a nice picture of the layer. Okay, so this is not enough in the case of MRI because you have constraints between the samples. And what we proved in 2 papers was that we could obtain the same result by adding a projector here on the space of admissible curves, pi of x. And this projector, if you want to know how to design it for MRI, I refer you to this paper in IEEE TMI. And if you want to know how to solve this efficiently, you can have a look at this paper in constructive approximation. And in what follows, I will let MK denote the mapping which to pi associate the case iterate of this iterative process. And so here I will show you typical result obtained by this algorithm to generate an MRI sampling pattern. So we start from just a radial pattern, and we let the scheme run. There it's multi-resolution. So you will see the trajectories moving and progressively cover the space with a given radial density that is more dense at the center of the K-space than at the other space. And these trajectories are really uncommon in the literature, but you can actually implement them in practice. And we did this. And here are the results. So those results were published recently in Magnetic Resonance in Medicine. Here you have the reference image. Here you have the sparkling result. And you see that the quality is quite good. And it possesses less artifacts than the result obtained with a spiral trajectory, for instance. And here there was an acceleration factor of 16, meaning that for this in vivo acquisition, taking this image was 16 times faster than taking this image. Okay. So when we published this paper, we were really happy. Like we felt we were the bosses of sampling in magnetic resonance imaging. We felt that we dominated the field, and then deep learning came, and we had to revise our conclusion. Okay, so now I will try to review a bit what has been done with deep learning to optimize the sampling and reconstruction process simultaneously. And what I will tell you was also a joint work with Alban Gossard and Frédéric de Coil. So the limits of theory are rather clear. First, we consider 2 simple signal classes. For instance, we consider the space of band-limited functions or a space of sparse functions in some orthogonal basis, but this is too simple. The second problem is that the reconstruction methods are too simple also. And we now know that the neural network reconstructions are superior to L1 minimization. A second fact that changes the landscape is that we now have databases available, like the FastMRI Challenge, OpenFMRI. We have super good softwares like TensorFlow, PyTorch, or CUDA. And this raises the question, can we design dataset adapted sampling pattern? The answer is yes, and there has been quite a lot of activity in the last 3 years about this problem. And mostly, I could see two different approaches. One that I would call best subset selection methods, and the second one which are continuous optimization methods, and I will review them briefly. So in best subset selection methods, you are given a set of images U and a finite set of trajectories, T1 to TL. They are admissible. And I will assume that the time to sample the trajectory TL is small tl. Okay. And we are also given a fixed reconstructor R of yx. And the question here is how to find the best union of trajectories to obtain a result, a reconstruction result. And so to find this subset, you can formalize the problem as follows. So you want to generate a sampling set X as a union of trajectories. And what you are looking for is this calligraphic L, which is a subset of indices. And you are given a total time budget capital T, and you want that the sum of the sampling times is less than this T. Okay. And then your cost function is the same. So for instance, here is an illustration of one algorithm that you can use to solve this. Imagine that you can only sample horizontal lines. So this would be your T1, TL would be all the horizontal lines. And what you can do is probe every line, reconstruct all your images using this line only, and pick the line among those lines which provides the best signal-to-noise ratio. So this will give you one line that you can keep in memory. And then you redo the same process and same process again. And after a while, you will generate some sampling pattern, which is hopefully is good. And you generate it in a greedy manner. Okay, this would be one way to solve this problem, to find an approximate solution to this problem. But of course, this is extremely time consuming. This approach corresponds to this paper by the group of Sever. And there are other approaches in the pipeline that have been published recently. But they are all very time consuming. I also want to mention this paper which is remarkable because it was in 2010. And I think that the ideas there were quite good and the group was quite visionary. And as a summary of this method, they proved to have some assets, like they can automatically infer efficient sampling pattern. And it is efficient if you have a sufficiently small number of feasible trajectories. The problem is that it's very computationally intensive, and there is research to be done to improve this. It is combinatorial, so you have plenty of spurious minimizers. And also you have a rigid choice of trajectories. And finally, it's hard to jointly optimize the reconstructor and the sampling set. So this leads me to continuous optimization of the sampling and the reconstructor. And there are quite few works. I only spotted 4 in the literature. So this paper here is quite important. It was published recently in Melba, called Pilot, by the group of Bronstein. And there is another very nice preprint by Jeffrey Fessler with a method called Bjork. And we also have 2 preprints. So the idea here is to both optimize the reconstructor and the trajectory. And the reconstructor is parameterized by some weights W. So you can think of this RW as a neural network, for instance, an unrolled neural network. And you can think of this X as a sampling pattern. And there you see that the difference compared to previously is that X is free to live in all the admissible trajectories. And this super complicated problem can actually be attacked with the modern tools, such as automatic differentiation, stochastic gradient approaches, a very good GPU, and a few weeks of computing times. And well, in a sense, you solve exactly the problem that I phrased at the beginning, and you try to solve it with brute force computing. And it is a hard problem. We proved it. We proved that this function, if you fix the weights here, this function j of dot w possesses an exponential number of spurious minimizers with respect to m, the number of sampling points. So there are plenty of spurious minimizers, and it will be hard to avoid them. Then we showed also that we could leverage oscillations by using large datasets of signals, stochastic gradient descents to avoid escape critical points, and use specific preconditioning techniques. Okay, this is a recent preprint that we had. And then to avoid those spurious minimizers, what we proposed, there are other solutions, but is to try, instead of optimizing the sampling pattern, to optimize the underlying density pi. And this density in itself can be parameterized by some vector z in RQ in small dimension. And from the density pi of z, we can generate a feasible sampling set using this mapping MK, this complicated mapping, that generated these trajectories. And okay, this is a new optimization problem. And it has a few assets. So here is the illustration. This would be the parameterization z. For instance, you can parameterize the density with splines. From those spline coefficients, you generate a continuous density pi. And from this, you generate a feasible sampling scheme, x of pi of z. And the nice thing is that it automatically generates nicely distributed sampling patterns, because you have this mapping MK. You have a regularization effect, because you are working over a smaller dimensional set. And experimentally, it really improves the convergence speed. We need about an epoch to obtain convergence, while you would typically need 10 on the fast MRI challenge if you didn't have this additional mapping. Okay. So, sorry. So here is an example of result. So I will compare those two sampling schemes. So this one is a very nice sampling scheme. It's dense at the center with a channel, it's radially decaying. And we trained a neural network to reconstruct images with this sampling scheme. Then we jointly optimized the sampling scheme here with additional trajectory constraints, as you may see. And the neural network reconstructor. Then we compared the reconstruction results. And what we saw is that these trajectories here provided an improvement of about 1 decibel compared to this trajectory on the fast MRI need challenge. And this is for a subsampling factor of 4. Okay. So we are now in the process of evaluating the results more seriously. And so, as I said, we have about a decibel, a gain of a decibel on the fast MRI challenge with a single coil, which is significant. And the computing time was about 24 hours to obtain this result. So this is nice. But then we wonder, is there a real gain? And what seems to get out of the analysis is that we tend to improve the large structures. In the fast MRI challenge, you have a lot of verticals edges like this, but not really the details. And in fact, on a typical slice, this would be the error for our optimized scheme and for the radial scheme, which is already very good. And here we have a 2 decibel improvement. And if we take note of range slice, we get a -2 decibel drop. Okay, and so there the radial sampling pattern was better. So what are the advantages of this joint optimization of the sampling scheme and of the reconstruction? So we don't have any ugly theory. If you go to compressed sensing, this is really complicated. You can jointly optimize the sampling and reconstruction pattern. You have a good average improvement of about a decibel at no additional cost. And this is somewhat the death of intelligence because you solve a super complicated problem just with a computer and massive computing power. But I think that there are still many research opportunities there. First, we need to improve and accelerate the convergence of iterative schemes and to avoid spurious minima. We should make it scalable with 3D, 2D plus time, 3D plus time. We should conduct a rigorous evaluation of the performance and account for more accurate models, for instance, account for the sensitivities or off-resonance effects, and finally test this in real conditions. Thank you very much, and I'm open to any questions. Goodbye.